Hi, thanks for joining me. Today I'm going to be revisiting an old video in which I claimed to have proved that the nth root of 3 was irrational using this sort of non-standard proof. But shout out to Noah who pointed out that in fact the proof wasn't a proof, it was completely invalid. The main sort of step in the proof just didn't work, and I didn't actually say or do what I claimed to have been doing. So I've removed that video, but I've managed to alter the proof to make it work, and that's what I'm going to present today. So it's not the standard one in which you assume 3 to the 1 over n is rational, then it equals a over b, where a and b are co-prime, and then you do some stuff and show that a and b are actually not co-prime. This is going to be a different one, and I'm going to be proving it by contradiction. Okay, so let's get stuck in. Let's suppose that the nth root of 3 is rational. Okay, so then 3 to the 1 over n equals a over b, where a and b are natural numbers. Now I'm not going to insist that they're co-prime. You can if you want, doesn't really matter for this proof. Okay, now I'm going to let that set S be the set of natural numbers x for which x times 3 to the t over n is also a natural number, and that's for t equals 1, 2, all the way up to n minus 1. Okay, so this is some set, and firstly, like I did before, I'm going to show that S is non-empty. Okay, and I'm going to do that by showing that b to the n is in S. Okay, well let's see why. Firstly, b is a natural number, so b to the n is certainly a natural number, so it meets this condition. I just need to check it meets this condition. Well, so b to the n times 3 to the t over n, that's the same as b to the n times 3 to the 1 over n all raised to the power of t. Okay, and now this thing here is b to the n times 3 to the 1 over n is a over b by assumption to the power of t. And now just using basic exponential rules and whatnot, we can write this as b to the power of n minus t times a to the t. Now because t is one of these numbers here, it's strictly less than n, so this thing here will be a natural number, which means b to the power of a natural number, well that's a natural number, and here we've got times a to the t. So this thing here, times a to the t, this is also a natural number. So we've got a natural number times a natural number. This is certainly a natural number. So b to the n is in S, because it satisfies this condition, and of course b to the n is a natural number. Wonderful. Now the fact that it's b to the n doesn't matter. All I actually need is that S is non-empty. Okay, so I've just proved that S is non-empty because b to the n is in S. Now what I'm going to do is let d be the smallest element in S. Okay, and now this certainly makes sense because S is non-empty and it's a subset of the natural numbers, which means it certainly has a minimum which is in the set. Okay, so d is the smallest number in this set, and now to get my contradiction, I'm going to show that in fact there's some smaller number than d which is also in S, which of course doesn't make any sense. Okay, so and I'm going to define this number. Let's call it y. Okay, and it's going to be 3 to the 1 over n minus 1 times d. I claim that this number is in S and it's smaller than d. So there are 3 things I have to check. Firstly, I need to check that y is a natural number, so it meets this condition. Then I need to check that y times 3 to the t over n is also a natural number, so it meets this condition, where t is one of these numbers. And then finally, I have to check that y is less than d. So those are 3 things I have to check, and if I can do that, then I've found my contradiction, and that's the end of the proof. So let me work down that list one by one and show each of those are true. Okay, firstly, y is... Oh, I just rubbed out what y is. Let y was 3 to the 1 over n minus 1 times d. Okay, firstly, let's show that y is a natural number. Okay, let's expand y. Well, y is 3 to the power of 1 over n times d minus d. Now, by our assumption, d is an element of S, which means that d times 3 to the 1 over n, i.e. this thing here, is a natural number. So this thing here is a natural number, and of course d is a natural number. So this is certainly an integer. Any natural number minus another natural number is an integer. So we just have to check that it's positive, but that's quite clear. D is positive, so I just need to show this thing here is positive. But 3 to the 1 over n minus 1 is positive, if and only if 3 to the 1 over n is greater than 1, and that's if and only if 3 is greater than 1 to the power of n, just by raising both sides to the power of n, but of course this is always 1, and hence 3 is bigger than 1, which is obviously true. And thus this thing here is positive, so I've got positive times positive, so that means that y is positive, and I've shown it's an integer, so that means that y is a natural number. So that's this one done. Now let's move on to the second one and show that y times 3 to the power of t over n is also a natural number. Okay, so what's y times 3 to the t over n? Okay, that's just 3 times t to the t over n times 3 to the 1 over n minus 1 times d. Okay, now expanding this out, that's 3 to the t plus 1 over n times d minus 3 to the t over n times d. Now, because of this property here, essentially, each of these numbers is also going to be a natural number. Okay, because remember d is an s, by our assumption, it's the smallest element in s, and because of this thing here, well, this thing here is clearly a member of s, because of this property here. And now this one here, you may be a little bit skeptical as to why it's an s, because you've got t plus 1 here and not t, but hopefully you can convince yourself that it is an s, because if t is less than n minus 1, i.e. it's 1, 2, or any number up to n minus 2, then t plus 1 is some number less than or equal to n minus 1, which means that this thing here is an s. So all we need to do is check that in the case t equals n minus 1, this thing is an integer. And to do that, it's quite simple. If t equals n minus 1, we've got n minus 1 plus 1, which is n, divided by n, which is 1. So we've got 3 to the power of 1, which is 3 times d. And d is a natural number, so 3 times d is a natural number. Anyway, we've got two natural numbers subtracted from one another. So like before, we know that this thing here must be an integer. But because we showed that y was positive, in fact y is a natural number, it's positive. So this thing here is also a positive number, so positive times positive is positive, and because it's an integer, it means that y times 3 to the t over n is also a natural number. So that means that the second bullet point is done, and the last thing we need to show is that y is less than d. So y is less than d, and that's if and only if 3 to the 1 over n minus 1 times d is less than d, while dividing both sides by d. That's if and only if 3 to the 1 over n minus 1 is less than 1. And that's if and only if 3 to the 1 over n is less than 2. And that's if and only if 3 is less than 2 to the n. But because n is bigger than or equal to 2, this thing here will always be at least 4, which means this thing is certainly satisfied. So that means that this number here, this inequality here holds true, and thus y is less than d. Okay, so I've proved each of these bullet points holds. So I've shown that y is in s, that comes from these two things here. And I've also shown that y is less than d, which is obviously a contradiction because d was supposed to be my smallest element in s. So I've arrived at a contradiction. That means my original assumption here must be false, i.e. 3 to the 1 over n is not a rational number, i.e. the nth root of 3 is irrational. I hope you have enjoyed that video, enjoyed the proof as well. It's quite a cool one. Of course, if you're trying to prove it as quickly as you can, you use the standard proof. But I thought this one is quite a cool one, and I'm not sure if many people have used this proof before, or if it's a new one. I don't know. Anyway, I thought I'd include this for your entertainment. Anyway, if you wanted to, you can adapt the proof slightly to show that the nth root of any non-power of n is also irrational, and I'll leave that as an exercise to you. And anyway, just if in the future any videos I do make there are mistakes, please do put it in the comments, let me know, and I'll try and rectify it, or in the case where it's unrectifiable, I'll just make a new video about it, like today. Anyway, that's all for now. If you did enjoy the video, please do subscribe. We're almost at 200 subscribers, hopefully going to get there by the end of August. That's all for now. Catch you in the next one. Have a great day.